using visualization for analyzing data and defining and understanding the analysis task is therefore important. There are many choices for visual representation of data, and we need to be able to distinguish the good ones from the bad ones. Therefore, evaluating and validating visualization approaches is an important component. That's a challenging problem, however. Purely computational approaches are relatively easy to assess. We can measure execution time, memory use, and so on, and then compare them to other approaches with similar measures. Introducing a human analyst in the loop makes these comparisons more difficult. Next, we will discuss some related disciplines and also subfields in visualization. Visualization is sometimes mixed up with imaging or image processing, since both fields deal with pictures. However, their goals and workflows are very different. In visualization, on the left side, we start with a dataset and then design and implement an interactive visual representation of that data for human interpretation. In imaging, on the right side, we start with a picture and use computational approaches to automatically extract data. So, in visualization, the end product is a picture and it's meant for human consumption, and in imaging, the start point is a picture, but it's processed computationally. Data visualization has two subfields. Information visualization deals with abstract data that does not have a representation in the real world, whereas scientific visualization deals with physical data that has a real-world representation. So two fields use different approaches and methodologies. The information visualization example on the left shows stock market data. It doesn't have a visual representation that we could readily use, and we have to invent a representation. The example uses a tree map to show a hierarchy of the sectors in the stock market and a red-green color coding to indicate how individual stocks performed on a selected day. Green indicates they went up, red indicates they went down. The brighter the hue, the bigger the change. The challenge here is to design a visual representation that can effectively answer specific questions about the data. The scientific visualization example on the right shows measured airflow data over a car. It already has a representation in the physical world, since the model was created by measuring or simulating the real world. Therefore, we don't have to design a visual representation, but the challenge rather is to visualize our model as precisely as possible. Visual analytics is another related field. Its goal is to achieve a tight integration of visual and automatic data analysis methods with database technology for a scalable interactive decision support. In essence, it really aims at bridging the areas of artificial intelligence and intelligence amplification. It uses an iterative workflow. Analysts start at the left with their data. Based on their task, they use visual data exploration, data mining, or a combination of the two to gain some insight and extract knowledge from the data. Through a feedback loop, using their new insights, they get back to the starting point and repeat the analysis cycle until they have completed their tasks. Visual analytics integrates scientific disciplines to improve the division of labor between the human and the machine. Machine-focused disciplines include statistical analysis, data mining, data management, and compression and filtering. Human-focused disciplines include human cognition, perception, visual intelligence, and decision-making. Information visualization, graphics, and human-centered computing have components of both machine and human-related disciplines.